Okay, so somehow when prepping for the second half of this week, I had it in my head that there was Monday was part of the lecture series. I don't know. I mean, I knew according to the schedule I put out there that there wasn't any lectures after today. But as it happens, the material that we were going to cover today, this is why I gave a little bit more extra time to discussing preparing for the exam. But as it happens, the material that we covered that we will be covering in this video is three aspects of the same item. So, we covered basically enough in person to work any problems, but we're going to go through this stuff all through, go ahead and go through the material in process, and then and if you have any questions, make sure you email, but you should have all the tools that you need in order to tackle double slit experiment, diffraction, diffraction gratings, and Young's, or not Young's, but the single slit experiment. Okay, so I'm going to pick up a quick recap on Young's double slit experiment, where we have the two slits acting as two light sources. Those waves produced by that diffraction interfere, creating a pattern on the screen. And so we demonstrated some geometry based off of that, where we labeled the individual fringes. That's the bright marks. There's also the dark fringes, but if you understand the light fringes, you understand the dark fringes. And the light fringes are where you have constructive interference, whereas the dark fringes are where you have destructive interference. The key important values that you need to know about any one of these type of slit combinations is the slit width, the slit distance between neighboring slits, and the distance from the central maximum along the vertical axis from the central maximum. We also label here the distance from from each source by the distance r. This is a means to an end, so you don't need to really know what R is, R1, R2 for a given value. But again, the interference patterns, you have the bright fringes, you have dark fringes. We're going to use integer numbers because you can count the specific fringes, and they are evenly spaced. That's a very important factor when it comes to looking at the interference patterns on the screens, so that they are evenly spaced. And this applies to double slit, to diffraction, and even to single slit, even though there's a couple features of single slit that are slightly modified. Note again that the m equals 0 is the bright fringe. So we have this this quiz that we did actually on Wednesday, where we said what is the difference between the path lengths for two radii and whether or not they perform constructive or destructive interference. So I'm going to pause this for a second, or recommend you pause if you want to rethink about this before I put up the answer. And if you've paused it and you're coming back now, the answer is going to be this is constructive interference, because of the fact that we are looking for well, in this case, the question says, well, what is the difference in those two radii? The difference of those two radii is going to be 3 lambda. That's a whole number, so this is going to be constructive interference or bright fringe. So what is the geometry for this? Well, we can look at the configurations. We know that there's a slight path length difference. You can see this over here. I demonstrated this in lecture. And there's a slight difference between these two path lengths to that bright fringe, and that distance right there, delta r, is going to have to be, in order for it to be bright fringe, aka constructive interference, has to be an integer number of wavelengths, so m equals 1, 2, 3. You can include 0 there, but that just takes you to an angle horizontal to the path between the slit spacing and the screen, aka that would represent the central maximum. So considering the geometry here on the left side, you can see that you have the distance between the slit the double slit device and your screen, that distance is length L, and the central maximum is at y equals 0, so the distance to the whatever bright fringe you're looking at is going to be L times the tangent of the angle between the average angle between those two neighboring slits, and so that gives you a y sub m equals L tan zeta m, and where m here is, as this page shows, is going to be the mth fringe. So if we are looking at this fringe to the third order fringe, as you can see here, that would be the m equals 3 or y sub 3 fringe, distance being from, again, the central maximum. L is the length of the distance between the slits and the screen. Usually L is going to be significantly larger than y sub m. What is the path difference there? That's going to be that delta r. And over here looking at this, we know this distance here, we know this distance, we know the distance between the two slits, we know the short path difference is m times lambda, so we can work out that the angle of that is going to be sine of theta times the distance there, where m lambda comes from that delta r. Again, your m values are 0, 1, 2, 3. For m equals 0, your angle is going to be 0, and so you're going to have no distance, no path distance. Tan of 0 is 0 over 1. What are the positions of bright fringes on the screen for a double slit? Well, y sub m, once you combine these two equations, where we're assuming that the small angle approximation fits, sine of theta is equal to m, and tangent of theta is approximately sine of theta, which is approximately theta. And so those two, we combine the approximate sine theta to replace this, and gives you y sub m, your distance, in terms of just your which order maximum, m, the lambda, which is the wavelength of the laser or the light source, L is the distance against from the screen, and D is the small distance between those two slits. Again, L is going to be the larger value of the set of numbers in your in a problem, for example. The angles given to the bright fringe are sine theta of m equals to m lambda divided by d, and as I keep pointing out, m is an integer. So let's see here. So we worked this problem in class, and it's the light from a helium neon laser. You apply those equations, this equation above, y sub m, m lambda L over d, and you get the fringe numbers m equals 3. And then once you apply delta r equals m lambda, you get delta r is 1.9 times 10 to the minus 6, or 1900 nanometers, if you will, or 3 wavelengths. This is going to be demonstrated in your worked examples that'll be posted up on D12 by the time you are reading this or listening to this. So here's where we pick up. What is the distance between any given fringe spacing? Well, it's a constant value. It's a constant value because y equals m plus 1 minus y equals m is replaced by m plus 1 minus m in those expressions, and the m terms cancel out, and the distance between the fringes are just simply delta y equals lambda times L divided by d. So can we use that for a problem? And the answer is yes, for a double slit. What is the wavelength of light if we use a double slit interference pattern observed on a screen 1 meter away from the slits? They use behind, and a lot of times when they write these questions, and what they're basically saying is beyond the slits, where the slits are as the source and you have a screen projecting onto the screen. But the two slits are spaced 0.30 millimeters apart, so in that case, as I said, your length L is 1.0 meter. That's the largest value usually, and your distance between the, I was about to say displacement, between the two neighboring slits of the double slit is 1/3 of a millimeter. And they say one particular fringe to the center of the 9th bright fringe, which I didn't really care for that wording, but you can work out that the 9th fringe away corresponding 1.6 centimeters. This is a fringe distance between each neighboring fringe as 1.78 10 to the minus 3 meters. Then we plug this value into the expression from above, delta y lambda L over D, and solve that for the wavelength, plug the values in, and you get 530 nanometers. Is that reasonable? 530 nanometers is greenish, probably in the green to yellow band. But basing this off of your, let's say, your experience using diffraction grating, this would be where the 1 meter, but probably has a very, well, the distance between the two slits is very far apart. 0.3 millimeters is a lot larger distance than what you were seeing with diffraction grating, where they were on the order of 1.6, 2.0 times 10 to the minus 6 millimeters, so, or meters, which is 10 to the minus 6 is micrometers, so it's an order of magnitude higher, 10 to the third higher, well, 3 orders of magnitude. So you get wavelength of 530 nanometers. Again, this is a reasonable result at the very least because it's in the visible spectral range, so for consideration. So here we have another quiz to consider, and what you'll do is you can pause this and think about it before I give the answer. The light of wavelength L lambda 1 illuminates a double slit, and interference fringes are observed on a screen behind the slits. Then you change the wavelength, you change the laser or the light source to lambda 2, and the fringes get closer together. And so the question is, how do the wavelengths compare to each other? Because the fringe spacing delta y is directly proportional to the wavelength, when you change the delta y to a shorter value, then you get a shorter wavelength or a smaller wavelength. So next we talk about diffraction of light. It's a lot like the double slit experiment, and so we should be able to get through this pretty quickly. Diffraction of light, you have these closely spaced slits, which each act as a source, and you can see the diffraction acting at each of those points, and they've got the little the little path differences that are enumerated here. And each of those slits is closely spaced. There's a distance of d between, and again, we mark from the center of a slit to the center of the neighboring slit to get that slit distance. And just like double slit, bright fringes will appear evenly spaced distances. However, and this is due to each wave from each slit constructively interfering at each bright fringe. However, a pretty interesting characteristic shows up, which is that in between these points, you'll notice that the bands are much more narrow, as opposed to the bright fringes being very wide for your double slit. They're much more narrow. And the reason is because there are more sources to interfere with one another, and so what they actually do is destructively interfere in these dark bands between each of the bright fringes. So that's, for what it's worth, there's that. What are the positions of these bright fringes? Well, it's the same geometry, and so you end up with the same equations, and pretty much not much to say difference. Even when I was looking at the textbook and looking at the summary of equations at the back, it didn't, it showed them as being the same equation for the double slit and for diffraction grating, and I was looking for a way to say, well, for diffraction grating, this is the difference. There's no difference. The real difference, I guess you might say, is that for double slit, the value D is going to be significantly larger than for diffraction grating. Diffraction grating is going to be, 1,000 lines per millimeter, whereas a double slit experiment will probably be 2 lines per a centimeter or something like that, or half a centimeter, per 2 millimeters. But you have a big difference between the size of the D's, but the equations are the same and you get the same results. So it's important that you are able to recognize those. But it's the same equations as the double slit experiment. How close all the neighboring slits are for a diffraction grating is going to affect the sharpness of the bright fringes. So if you've got as you increase the number of slits, you're increasing the number of sources that can contribute to destructive interference in between, and so you've got smaller and smaller peaks that are in the bright fringe band until you have just the single one peak when you have, as you can see, 4. That's light intensity. 150, 200. There it is. 2 slits, 10 slits, and then 50 slits in a short range. So let's do an example and consider the wavelengths of sodium. The diffraction grating is applied for a sodium lamp, and it provides that there are 2 bright yellow fringes that are projected onto the screen from the central maximum. The diffraction grating is given as 1,000 slits per millimeter, and the interference pattern is viewed on a screen that's 1 meter behind the grating. Don't let all those decimal places throw you off. That's still 1 meter, so this is going to be the length L. 2 bright yellow fringes are visible at Y values, 72.88 centimeters and 73 centimeters from the central maximum. What are the wavelengths of these 2 fringes? So we look at the configuration. We say, okay, well, the grating is 1,000 lines per millimeter, so we need to convert that by taking the inverse. 1 over 1,000, or 1.0 times 10 to the minus 6 meters once you convert from millimeters to meters. So it's 10 to the minus 3 millimeters per line, or between each line, or 1.0 times 10 to the minus 6, which is 10 to the minus 6, 1 micrometer between each line. Notice in the sketch I've got this drawn. You got your length L that's going from the diffraction grating over to the screen. The screen central maximum is the dashed lines. And what I've indicated is Y sub 1, that's the first order fringe. We're going to assume M equals 1 in this case. The first order fringe, 72.88 centimeters, or converted to meters. And then Y sub 1, 2, the second yellow fringe for the first order fringe of that color, of that wavelength, is at 73 centimeters. And so we assume again that this is the first order fringe for these values, and that's fairly safe unless the problem says otherwise. You can make that assumption. So according to M equals 1, M lambda d sine theta sub 1, we need to know the angle for each of those lines, and so we're going to look at the ratio from the tangent expression. And we'll do that on the left side. We'll do this for the 7288 centimeter line, and on the right hand side we'll do this for the 7300 centimeter line. We plug those values in, and the angle for the 7288 is 36 degrees, 0.085. Look how many decimal places we need to carry to make sure that we have good propagation of error. If you just did this calculation, you got set 36.1 from rounding from both of these, you will end up with the wrong wavelength. You'll end up with the same wavelength and assume that you got that right. So make sure that you're careful about that detail. Carry extra decimal places until you don't need them anymore because of rounding, because you're reporting the answer. Then we plug this into lambda equals d sine theta, and for the distance 10 to the minus 6, and the angle 36.085 on the left, 36.129 on the right. You end up with 5.8898. You round it with decimal places or the sig figs. That's 589.0 nanometers for your first yellow line from sodium, and your second yellow line from sodium is 589.6 nanometers. These are distinguishable lines. They are distinct lines, so they have to have 2 different wavelengths. Again, if you're working a problem that has this question, you got to make sure that you carry enough decimal places to be able to distinguish these 2. But other than that, that's pretty straightforward for that. Again, we're using the same equations that we used for the double slit experiment. How do these two compare? Again, this is just to demonstrate that your equations are the same. And really the only difference, it's not so easy to use the small angle approximation for the diffraction grating. So because for some of the slits, it's a rather, it goes outside of that and to help contribute to the destructive interference. But outside of that detail, we're using the same equations. So here's another quiz to consider. White light passes through diffraction grating and forms a rainbow pattern on a screen behind the grating. For each rainbow, what is the arrangement for your relative red side and violet side? So we'll pause for a second. As you may recall, if you did the lab portion, you did the diffraction grating for mercury for spectral lines, and we saw that they were actually symmetric around the central maximum. You had the violet that was closest to the central maximum, and then you had your your greens, and then your orange line, those two strong lines, and then a faint red line on the outside. And so having the red side and the violet side on the left is not universally true for both sides because it expanded outwards. So really the best answer in this one is going to be D. The red side is farthest from the center of the screen. The violet side is closest to the center. Finally, we're going to look at single slit diffraction and see how that goes. And this is where we introduce some interesting idea, because for a single slit interaction, you would think, okay, well, for a double slit, we're using two different sources. And for diffraction grating, we're just adding more sources to interfere on a point. But as it turns out, light, being as quirky material substance that it is, whatever, it's not substance, but whatever this phenomenon is, that displays wave-like properties, when it passes through a single slit, it shows an interference pattern. And that pattern is spread out horizontally, which seems counterintuitive, especially since the slit is vertical and narrow horizontally and vertically tall. So how is this possible if it is a single source for diffraction? And the answer is, we look back to a guy named Huygens from the 17th century, and he developed this idea of wavelets where you can choose various points along a given pathway, evenly spaced, and use those as diffraction sources where the wave propagates circularly outward. And after the appropriate time for the wave to reach the next wavefront, you find that the wavelet has also met that wavefront, and in such a way to be tangent to that wavefront. And so the wavelets actually act as a wave source of propagation. Now, this is a kind of a nifty little detail for drawing a wave pattern that goes outward for a circular source or a plane wave propagating forward. But how does that apply here? And the answer is, well, the slit width is still very large compared to the wavelength of light. And so you have this option for having all these multiple points that can be your new diffraction source for wave propagation outward, or your wavelet source. And so they propagate outward and form, form the new wavefronts as they go forward. And in image B here, you see them propagating forward to produce a central maximum, but they can also propagate outward and have a shared pathway that allows them to interfere constructively with themselves. And so you end up with this as you can see in this image, this really wide central maximum, and then these narrower, progressively narrower secondary maxima. And we draw that with a very big central maximum here. But as it happens, they're still evenly spaced. And so we can still apply the same formulas, only in this case, because it's a single slit, the variables are changing a little bit. So instead of slit distance or separation D, we're looking at the width of the single slit. and we're using A in that case. It's not clear why A is the choice. It's just the common way to go. P is going to be your integer values, and so 0, 1, 2, 3, just like you have with the diffraction and with the double slit, only instead of M, you're using P. And again, your length L is significantly larger than your slit width, A. And so there is one additional thing, that the central maximum does have a width that can be determined, and that is given by double the lambda times L over A, and the angles to the given bright fringe. There you go, you have that. And again, these are the same. It's the same problem. It's the same question. It's the same formulas. They just have a little bit different look to them because of the slightly different variables. But that's because single slit versus double slit. And you can apply the Huygens principle to the double slit and to diffraction just as you would otherwise for the single slit. So one last example, we're going to look at, again, the helium neon laser passing through a narrow slit on the screen, which is now, the screen is 2 meters separated from the slit. The first maximum on the diffraction pattern is 1.2 centimeters from the middle of the central maximum. And so how wide is the slit? And if we look at the calculations, so we got the lambda. L is the largest value, 2.0 meters. Y sub 1 is 1.2 centimeters. So we convert that. And we just use the simple relationship for the distance to the bright fringe, the first bright fringe. And that's given as 1.2 centimeters. Plug the values in. And the slit distance, the slit width is 1.1 times 10 to the minus fourth, or 0.11 millimeters. It's a very narrow slit, 1/10 of a millimeter effectively. But as you can see, it's a recycling of the same equation. So here you have a table where you can kind of see what the comparison is for these. And for diffraction grating, remember the diffraction grating is slightly different simply because the contributing wavelengths or the contributing sources along the diffraction grating may go beyond the small angle approximation. That's the only difference, but otherwise these are the same equations. L is going to always be the distance from the diffraction source to the screen. Y sub M for double slit diffraction, or Y sub P for single slit, is the distance along the screen from the center to the given fringe, and L is usually going to be significantly larger than your slit width or slit distance. Slit width is A, slit distance is D. And that wraps up wave optics. So hopefully, make sure if you have any questions about this and any comparisons, shoot me an email. Let's set up a Zoom meeting if you need to have a chat about it. But the concepts are pretty uniformly applied. This is the only material that's going to be tested on for these two chapters, and that should be all that you need in preparation. So again, any questions, please email. Otherwise, we'll see you on Wednesday.